Hello grade 10 students, welcome to our virtual class for the 4th quarter week 1. I'm Abigail Sarmiento, your science teacher. Our lesson for today is about behavior of gases. Most gases are invisible. We can name as many solids and liquids that we see around us, but not gases. It is only the very few colored ones like the black smoke produced by smoke bleachers that can be seen. Unseen gases are present, to name a few, in a bottle that seems to be empty, in the production of food by the plant, and even in playing our favorite sports. Can you play your favorite sports like volleyball and basketball without the ball sufficiently filled with air or gas? Even our very own existence requires the presence of unseen gases. We take in oxygen and we exhale carbon dioxide. Can we survive here on Earth without the desirable gases which support life? The volume of a given gas sample is directly proportional to its absolute temperature at constant pressure, Charles' law. The volume of a given amount of gas is inversely proportional to its pressure when temperature is held constant, Boyles' law. Gases have volume, mass, temperature, and exert pressure. From your daily experiences, can you enumerate some instances where these properties are shown? The warm temperature we are experiencing is from the heat trapped by the greenhouse gases, carbon dioxide, methane, and water vapor, to name a few. The basketball is filled with air, so it bounces while you are dribbling it. The same is true with the other kinds of ball. When you open a can or bottle of soft drinks, it fizzes because of the escaping dissolved carbon dioxide due to change of pressure. When the wind blows, it exerts pressure too. There are a lot of manifestations of gases, though we cannot see them. Gases have mass, volume, temperature, and pressure. Let us now be familiar with the units being used to express these properties of gases. Can you identify whether a unit represents volume or pressure or temperature? Below is the list of these units. Start familiarizing yourself with them. In your grade 9 lesson on living things and their environment, you made use of the lung model to explain the respiratory system. Do you still have the model with you? Try to use it again. What do you notice as you pull the bigger balloon that represents the diaphragm? Yes, the lungs expand. Let's try to explain it with the use of Boyles' law. Pulling the rubber balloon represents inhaling. As you inhale rather, the lung cavity expands, causing the pressure inside the lungs to decrease and become lower than the outside pressure. As a result, air flows from the higher pressure area, which is outside the body, into the lungs. Exhaling is the opposite process. When you release the rubber which represents the diaphragm, the balloon representing the lungs decreases in volume. This phenomenon happens during exhaling. When the diaphragm contracts as you exhale, it results to a decrease in the lung volume, increasing the pressure inside the chest cavity and causing air to flow out of the lungs. Try to breathe in and breathe out and mindfully observe what happens to your lung cavity. Interestingly, as you inhale and exhale, approximately 500 ml of air gets in and out of your lungs. Here is another thing that can happen which can be explained through Boyles' law. Have you observed the air exhaled by the fishes in the aquarium? It gets bigger and bigger as it rises because the pressure at the bottom of the aquarium is higher than the pressure near its surface. Where else do you see applications of the relationship between pressure and volume of gases? The relationship between the volume and pressure of gases at constant temperature was first stated by Robert Boyle during the 16th century. He performed an experiment wherein he dropped a fixed amount of air in the J-tube. He changed the pressure and controlled the temperature, and then he observed its inside the J tube. He found out that as the pressure is increased, the volume decreases. He finally concluded that the volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. Equation VA 1 over P at constant T and N, where V is volume, P is pressure, T is temperature, and N is the amount of gas. How will you read the above cited equation? It is read as, the volume of a gas is inversely proportional to its pressure. If temperature and amount of gas are held constant, it can also be read as, at constant temperature, the volume occupied by a fixed amount of gas is directly proportional to the reciprocal of pressure, 1 over P. Let's take a look at the equation again and try to change the proportionality sign A with the equal sign B, A, 1 over P at constant, or K. B equals K over P, thus K equals P. The latter equation is simply read as the product of pressure and volume is constant. Can you enumerate familiar events you observe in your community and household which are related with the volume-temperature relationship in gases? The sky lanterns we use in celebrating New Year, Christmas, weddings, and other important occasions operate on the concept of volume-temperature relationship. Have you tried releasing the sky lantern? It is like a mini hot air balloon. As the temperature increases, the sky lantern obtains its full volume and rises in the atmosphere. It rises and rises as the atmosphere increases because the density of gases decreases as gases expand due to the increase in temperature. This explains that the increase in volume and decrease in density cause the sky lantern to float in the air. The volume-temperature relationship in gases, K equals V times T, were determined by the name after Jacques Charles. In his experiment, Jacques Charles trapped a sample of gas in a cylinder with a movable piston in water bath at different temperatures. Jacques Charles found out that different gases decrease their volume by factors 1 over 273 per degree Celsius of cooling. With this rate of reduction, if gas will be cooled up to negative 273 degrees Celsius, it will have zero volume. Interesting, isn't it? Charles' law states that at constant pressure, the volume of a fixed amount of gas is directly proportional to the Kelvin or K temperature. Mathematically, Charles' law can be expressed as VA T at constant P, where V volume and T temperature expressed in Kelvin. Why is there a need to convert degrees Celsius to K? Kelvin is the basic unit for measuring temperature in the international system. It denotes the absolute temperature scale whereby 0K or absolute zero is defined as the temperature when molecules will have the lowest energy. Removing the proportionality symbol A and using the equality sign, the equation will be as follows. V equals K and T, or K equals V over T. Thus, in a direct proportion, the quotient of the variable is constant. If we are going to consider the initial and final conditions, you will arrive at the following equation. V1 over T1 equals K and V2 over T2 equals K, whereas V1 is the initial volume and V2 is the final volume. T1 is the initial temperature and T2 is the final temperature. If the volume-temperature ratios are the same in the initial and final conditions, then you will arrive at this equation. V1 over T1 equals V2 over T2. Are you familiar with the pressure cooker? The pressure cooker is airtight. So, low pressure builds up inside the pressure cooker as the liquids inside comes to a boil. The resulting trapped steam causes the internal temperature to rise more than what it can normally do at normal atmospheric pressure. Thus, the cooking of hard meat and fiber is done at a short period of time. The person who is credited with the determination of the temperature-pressure relationship in gases at constant volume is Joseph Louis J. Lustig. He deduced that the pressure of the gas is directly proportional to its temperature. This means that when the temperature of gases increases, its pressure also increases, or vice versa. Hence, we can state that J. Lustig's law as constant volume, the pressure of a fixed mass of gas is directly proportional to the absolute temperature. J. Lustig's law can be expressed mathematically as P and T at constant volume. It can be written as P equals KT or K over P over T. Since there is a direct proportionality between the pressure and temperature of gases at constant volume, it can be shown in this equation. P1 over T1 equals P2 over T2. And that is it for today's lesson. Please don't forget to subscribe to our YouTube channel, GAITF, or log into your account at lcms.gaitf.com so that you can answer the quizzes and activities given by the teacher. Thank you for listening.